Jie Yin from our department, Mechanical Aerospace Engineering. Dr. Jie Yin is currently an assistant professor in our department, and he got his PhD from Columbia University and did a postdoc, and then he was at Temple University for a few years before he joined us last year. And it feels like Jie has been in the department a long time because I see him all the time. So Jie is also an awardee, NSF Career Awardee, and he's also got the Engineering Mechanics Letters Young Investigator Award, if I'm right. Am I right, Jie? Yeah. So,
no, it's extreme. You're right.
Extreme. Okay, I thought it was an mechanic. Okay, Extreme Mechanics Letters. So he's going to show us some extreme mechanics stuff today, right? So Jie, take it away.
Okay, thank you. Yeah, thanks for the introduction, and also I would like to thank London Grace, to have to organize this seminar. So it's a great opportunity to share my research with a colleague here. So today I'm gonna talk about some our recent research or past research about how we can harness mechanical instability for functionality. So currently my group focuses on 3 areas. So one is about a multifunctional interfacial materials for energy saving and also water harvesting. So the other 2 are mechanics and design of mechanical metal materials and also soft robots. So my today's talk, I will part from each part of here. Okay, so here is the outline of my talk. So firstly, I'm gonna talk about surface instability, and after that, I'm gonna talk about structural instabilities. For the surface instability, especially, I'm gonna choose like 2 examples. So one is hierarchical wrinkling for multifunctional smart window. The other is extreme bulk denomination for stretchable electronics. After that, I'm gonna talk about the akigami for energy saving and also shape morphing, and also the soft robots using the BASTV for soft running robot. So let's first take a look at the smart windows, right? So you see in your room, your house, right? So you can see the blinds everywhere. So maybe in the future one day, so all the blinds will be gone. So they're gonna be replaced with a smart window. So you can see here in the office or in the auto. So the smart window means actually you can just push a button, and then so your window gonna be switched from clear to opaque to block the sunlight for energy saving, right? And also actually the smart window is a kind of switchable optical materials. So currently in market, they call it chromogenic materials, right? For example, like electrochromic or thermochromic. But the drawback of these materials are cost. It's high cost and also high durability, it's a low durabilities, and because of the material degradation, and also for the functionality is very slow switching time. You will see here, it's like stainless actually is no, it's gonna take minutes to switch from clear to opaque. So what is the challenge here? You're gonna fabricate large areas. Think about our high-rise buildings. Nowadays they are covered by large areas of windows, right? And then you should go fast switching time and long cycle life and also no manufacturing cost. So what we propose here is a possible solution is we're gonna design a new optical materials with simplified process, for example, wrinkling. So this we call it wrinkling-based optical switch materials. So wrinkles actually is everywhere, right, in your life. For example, the reason, right, and also for the dark. So how to get rid of these wrinkles actually make this dark looks very sad. Okay, so but scientists have started to take a look from positive way to how we can harness or making positive use of the wrinkles for functionalities. So this is a pioneering work actually in 1998. So this is what I did. Basically, you have a PDI mask. This is a silicon rubber. And now you just put it in the oven, right? And then you're gonna heat it, the PDI mask. And then after that, you're gonna deposit gold. The gold film is like 50 nanometer. And then after that, you just cool down the whole system, and then we will take out, right? Cool down the whole system and take out, you can see these beautiful micron scale patterns. These are called wrinkle patterns. Actually, it's not a surprise because the PDI mask has a larger CTE, right? So it's a coefficient of thermal expansion than the gold. So that's why the PDI mask, the substrate shrink more than the film. So you can see that wrinkle comes out. Right? Since then, so scientists have started to look at a positive way, okay, how we can use this wrinkle for functionality. So these are some examples, successful examples here, I'm including here. One is the stretchable electronics by Professor John Rogers in Northwestern now, right? The other is our colleague Yong Zhu. He did a stretchable nanowire conductors using these ideas. Also, the other areas, for example, you can use wrinkles to tunable wetting from hydrophilic to super hydrophobic. And also you can do the tunable transparency from transparent to opaque. Right? That's what give us some insights for the design of smart window here. So our goal here is we want to go beyond that. We want to do we call it the next generation multifunctional smart window. So that means it's not only to tune the transparency for energy saving, but also can collect water. But like what I said before, so the large areas of windows actually they can collect water from the morning dew, right? And then you can use for reuse that, right? So for the switchable optical properties, we concern like two things. One is the tunable transparency, definitely, right? That's for the energy saving. The other is the structure color. Maybe you can bring in the structure like the morpho butterfly wings, right? This is our structure color, not from the pigments. Right? So this could be used for energy absorption and also for aesthetics. And then for the water collection here, this is a very good example for the desert beetles, right? You can see on the shells, they have bumps. So these bumps they actually are we call it hydrophilic. They can absorb the water, right? The water condenses in the morning dew, and then they're gonna in the flat area these repel water, hydrophobic, and then they can collect water from the bumps, and then they can transport. Right? You can keep their head down, and then you can harvest the waters, from the morning dew, and then they can survive. Okay. So for the water collection, that's the two issues. One is the surface availability, and also the water condensation, right? So how much you can collect. The other, when you collect water, how you can do the transport, right? That means you're gonna control the droplets motion movement. So I would say this project is done was done by my PhD students. So it's Gaojian. So my proposal here is maybe we can use a dynamic tunable hierarchical wrinkle surface. So why I go to hierarchical? So first, you think about the lotus leaf and other surfaces in nature, right? It's all like hierarchical. The other thing is you have a larger surface area. So in that case, it could be enhanced the optical properties like that. So let me just show the results here. So that's what we generate that we call the two-level hierarchical wrinkle surface, right? You can see this is level one, the large wrinkles. So the large wrinkle, the wavelength here is 3 micron to 5 micron. The amplitude about like 500 nanometers. And then on top of the big wrinkles, right, we have a small wrinkle. These are nano wrinkles. The wavelength is around 400 nanometer to 905 nanometers, right? So and then you can see this is a profile here. Okay, so how do we generate these hierarchical wrinkles? Actually, the idea here is pretty simple. So just one thing is you're gonna do a sequential oxygen plasma treatment and also sequential strain release. So let me show you how we did this. So simply, right, you have a PDMS is strain free, and then you stretch to a certain strain, for example, 50%, right? And now hold it. And then you do the first time the coating. This is we call the oxygen plasma treatment on the top of the surface. And then the time here, T1 is like in the seconds, in the tens of seconds. After that, the top layer become oxidized, right? Oxidized. And then you can generate a layer like a nanometer, the thickness of nanometers, tens of nanometers. And now you release. See, you release, for example, not fully release. So release like a 20%. Now you can generate small wrinkles here. And now hold it, and then do a second time UVO treatment or plasma treatment. This time you got longer. So you got a longer treatment time. In this case, the oxidized right layer gonna be much thicker. In this case, right, tens of hundreds of nanometers thickness. And now you can fully release. See, let's see. You can see the hierarchical wrinkle. You can generate a large wrinkles and small rings on top of that. Okay. So, and then by manipulating different strain, you can release small and later, small strain, large strain later, or you can change the treatment time. So basically you can generate a lot of, hierarchical wrinkles. For example, this is it's a one big wave, three small waves. This is a one big wave, 6 waves like that. Okay. So then let's see what happens here. So for the optical property. So this is a sample of the wrinkle, right? As you can see, it's originally is opaque. It also have a structure color. So we call it iridescent color, structure color, right? When you stretch, it becomes transparent, right? That's because when you stretch, the wrinkle disappear, and then you can see it become transparent. But the interesting here is when we make it very clear, but you can still see this is the structure color. So we don't know, actually, we don't know what's going on. That means the structure color does not disappear. It still remains. And then we're gonna next thing, right? We're gonna do the do the characterization of the optical performance. This is the standard way, right? You can measure transmittance over the visible wavelengths, right? From 400 nanometer to 800 nanometer, right? So this is the blue curve here shows you when it's hierarchical wrinkled, right? So it shows average transmittance about like 40%. And then when you start to restretch, see here, 30%, 50%, and then it's become transparent. In this case, the transmittance go to 80%, become clear, right? So we also do the characterization of the structure color because this is a iridescent structure color, right? So that means you view at a different angle, it's gonna give you different color. So we can also do the measure the intensity with the wavelengths, and then you see this, the peaks means a different structure, different colors, right? At a different angle fine here. This is after, it's a wrinkled, right? After you restretch that, and then we do see these peaks. So that means the structure still remains. So what's happening here, actually? So now we started to using both experiment and also FEM simulation to see what's going on there. So in SEM here, so hierarchy one, you see the large wrinkle, small wrinkle here. And then when it started to stretch, right, 30%, you see the large wrinkle disappear. So that's why you see the sample becomes clear because the large wrinkle responds for the opacities. And then when you keep stretching that, so for example, now 50%, right, you can still see, wow, this is a nano wrinkle, the small wrinkle still remains. That's even, even see the crack here, right? So these cracks are become wider, even become wider because it's being stretched, right? It still remains. Now we're using FEM to say, okay, what's going on here? So basically we're simulating the whole process. I have a PDI mass, right? So the point A is before stretch. Now I stretch to point C, right? The large strain 3%, for example. And now I'm trying to release, right? And then I'm gonna add a new layer because it's a oxidized layer to the top. And then you see, and then when I release, it generates the wrinkles here, right? Small wrinkles. And then I just, the second time, I'm gonna increase the thickness of the layer to simulate the second oxygen treatment here. And now you can see the large waves, large waves comes in, right, compared to this, large waves. And then if you zoom in here, you see there's small waves here, okay? And now that's done, right? When now I restretch that. So now we restretch to point B, right? So we see here, okay, see, and then the large wrinkle disappear. I keep restretching, to the point C, right? That's 50%. You can still see that small wrinkles. You see the residue stress here. So that means we do have a residue stress remain if you're using the sequential treatment oxygen. So that's why we can see the iridescent color, structure color, right? These colors are coming from the nano wrinkles. Okay, that's we call it irreversible. Okay, so now since we are dealing with our optical property. So how about this kind of with water collections, right? One part is a control droplets. So I'm showing this video here. So this is a tilt angle. You put a 50 micron liter droplets, right, on top of it. So in the beginning, it's a pinned to the surface. And then if you stretch, right, mechanical strain to stretch, and then you start to slide. This is pretty simple because you have a driving force from the gravity, and also you have a retentive force, from the surface tension here, right? The two forces is balanced. But we're starting to stretch, right? So the gravity force does not change, but the retentive force reduce because it becomes smooth, right? So in this way, you can break the balance and then to start to control the pin and the stop, right? Pin, stop, and slide. And then in this way, you can control the droplets very well. Okay, and later we can see this is a show where we show the wetting property here. So this is compared to the non-hierarchical wrinkle surface. That case is a very large degree of anisotropic wetting. What I mean here means that if you measure counter angle, right, along the parallel direction and also perpendicular direction, this is our wrinkles, you have droplets here, right? And now you can see the angle, there are large difference. But for hierarchical here, we see the parallel is 138 degree, 135 degree is very little, right? There's a difference. And now the interesting here is that this guy is unstable. If you just vibrate a little bit, and then gonna be collapsed, to 180. So this angle gonna be reduced, and then to show increase a little bit, degree of anisotropic wetting there. And then we're gonna see, okay, how we can do the water condensation on this wrinkling surface. This has been done in the environment SEM. So we have put our sample. The samples are fixed on the thermoelectric cooler, right? So I put on the stage and then put in the environment SEM and then do the temperature here. So here is about about 5 degrees C here, right? Let me show you the result here, right? So we see some droplets, is smaller and then are tiny, right? So the droplets actually gonna nucleate at the valley, and then also they're gonna nucleate sequentially. Let me just show you the process here. If we see with the time, right, you can see this is the droplets, right? It's also already considered there, and they're gonna grow, right? So you can see if we see the counter area, this area does not grow. So they just grow that volume, on top, and then another critical volume gonna collapse, okay? And if you take a look at those tiny droplets here, in the valley, right? This is the wrinkle, the valley here. So they can nucleate from the valley, and then they're gonna grow. So because of the wrinkles, right? They cannot grow, it's kind of large barrier from two sides. They can only grow along the wrinkles, you see, along the valley, and then become like elongated like that. So this is pretty much similar to the cells, right? If you put cells and then grow the cells in the wrinkle surface, they're gonna be elongated along the wrinkles. So still, we are still working on that, and we hopefully will have more results to report about this. So this is the first part we are talking about hierarchical wrinkling. And then, so basically they have for example, right, Professor John Rogers, they have used this wrinkle method to do the design structure electronics, right? So this is their first generation. They can only deposit the silicon nanoribbon, right, on the PDI mass. They can only stretch like 10%, okay? So now how we can, increase this stretchability? So they propose another way. For example, I can use constrain the barcode denomination on soft substrate. This is their idea. They have a PDI mass. This is you see the purple lines, right? These are the adhesion sites. So and then this area is non-active. That means non-adhesive. So now you transfer printing your nanoribbon on top of it, silicon nanoribbon on top of it, right? And now you stretch your PDI mass and then release. That's what you're gonna observe. These beautiful patterns, right? This beautiful, denomination you can see exactly here. And now that's beautiful, right? And now they started to stretch that. So they find actually when you stretch more than 50%, for example, 53%, you can see the cracks here. So that's pretty good now, because if you're using wrinkling, you can only stretch 10%, but now you can stretch 50%, right? So actually, when we saw this, we were thinking, okay, how we can further enhance the stretchability to go to the extreme, right? The other thing is, when they make these patterns is so complicated because you're gonna involve photolithography and etching all together to the adhesion sites, right? How about if we remove, right? I just remove these adhesion sites, I just PDI mask, because PDI mask itself is adhesive, right? How about I just directly, deposit the nanoribbons on top of it, and then that is released. What will happen here? So that's our idea here. We call it spontaneous barcode denomination soft robots. So this has been done, my student is shooting. And then, so we have a elastomer, it's very similar. How we generate the ribbon here, we have a shadow mask. I put a shadow mask and I do the thermal, the thermal coating, right? So thermal coating here, and then I put a shadow mask, and then after that, I just remove my mask and then generate the ribbons, right? I can control the ribbon width. Here is W, this is my ribbon width, and I can release that. We do see the barcode denomination, right? So like periodic barcode denomination is the one that Professor John Rogers has done, right? But surprisingly, we also see the cracks. So they didn't see cracks in ribbon, but in our ribbon, we do see the cracks. So what's happening here? Actually, it's not a surprise, because think about, right, you are released strain horizontally, so the transfer direction you're gonna tension, right? Because this is compression and this is tension, right? So where's the tension, and generate the cracks. And now we see, okay, now how about I do increase my deposition thickness, right? I forgot to mention this is a gold. Actually, this gold is a 50 nanometer gold on the PDI mask. Now I increase the coating thickness, go to 40 nanometer, 80 nanometer, cracks disappear. So that's making us, okay, maybe, the crack is maybe related with, you can manipulate, right? Crack with the thickness. So, but the science problem is, so how we can, to predict this, we call it the width of fragments. You can see these are fragments. So between them, there's a distance, right? So I think about how we can predict this width, because if we know the width, and then we can design to avoid the cracks, okay? So this is This is the idea, you know, for the to predict the average width. I call it the average, right? The average width of the crack fragments. Think about how film and substrate and structure, you start to stretch, right? And now if you stretch, you can think about the stress gonna be occur in the film, right? So you can see the boundary here. So in the boundary, you see the boundary, two boundary, free boundary, right? So then the stress go to zero, and then you're gonna increase in peak in the middle, right? And now when the stress, the maximum stress is larger than the fracture strength of a thin film, are gonna be break in the middle. So that's our assumption. If you keep stretching, they're gonna break, you know, 1 to 2, 2 to 4, like that. So that's our basis assumption. So based on that, actually we can predict the average crack fragments D, the fragments with D. So you see here, D is really, you know, here is a linear proportional to a thickness, the thickness of thin film thickness, and also inversely proportional to your substrate Young's modulus and also your pre-strain. Okay, so now we start to use this to explain what we have observed in experiment. So you see, for this, right, I can use this formula and then to predict, right? So the D fragment, D should be around like 10 micron. Think about my shadow mask. This mask with about like 22 micron, right? So larger than my crack, the fragment. So that means you should see like two or three cracks. So we do see 2 or 3 cracks here, right? So now if you go to, thickness go to 40 nanometer, so the D give you is a predictor, right? So it go to like 27 micron. Think about, right? So your shadow mask is 22, it's smaller than your 27, so that's why you don't see the crack. Same thing here, it's smaller, right? So then it gives us an idea. I can design the crack-free ribbons, you know, by using this. If my ribbon width is W is smaller than I predict the fragment crack width, and then I can use this to design. So then let's see go Xray. Okay, so for example, silicons, right? They have definitely this is not a single crystal, it's amorphous silicon because we're using the thermal deposition on the equal flux here. So we can pre-stretch the equal flux for 120% and then deposit the amorphous silicon, right? It's still brittle and then gonna release, right? So this thickness is about 25 nanometer. So you can see, that's surprisingly actually, you don't see any cracks. Actually, you see here on the top, the waves, right? Because at this position, you're gonna be under tension, right? That's how the cracks gonna be occur here. So if we measure the geometry, we can find out the maximum strain in the film is about 1.2%. Okay, similarly, I can do the gold, right? I can stretch my equal flux to 400% and then put a gold nano coating, right? And then release. You see, we still didn't see any cracks here, right? So and then you can measure that the maximum is 3.2%. I want to see, right, from literature, so the fracture strain for gold is about 5%, for silicon is about 2%. It's all below the fracture strain. That's why you didn't see the cracks here. So if you compare these two numbers, maximum strain is 1.2%. I mean, the pre-stretch, right, the stress strain is 120%. So that means you can stretch this guy, you know, to 120%. And the gold here, crumble one, go 400%, right, without fracture, right? And then, so that's pretty good, right? So you can see these two numbers, right, is 100 times smaller, right? That's why that's the idea for structural electronics here. And then let's see what's the advantage of Barcode denomination versus the wrinkling, right? So we do the simulation here because simulation we can manipulate our interfacial toughness. So that means adhesion strength. I can make adhesion strong and weak. So if it's strong, right, it's harder to denominate. You can see the wrinkles comes out, right? If the adhesion is weak, and then let's see we see the Barcode denomination here, right? And then we can see the pre-strain 10% and 20% show here. Let me zoom in here, right? You guys cannot see the string contour here. For this two, the peak strain you see here, right? This one is a positive, right? This is tension. So here the bottom is a compression here. So the peak one is 0.17%. We have a strain of 20%. Okay, pre-stretch strain is 20%. For the wrinkles, right? So here is interesting. Here is on here. See, here you see this is 2%. The last strain, because this one is you see here, right? Is 10 times larger, right? The wrinkling, the peak strain is 10 times larger than the Barcode denomination. And if you compare this, right, it's 0.2, around 0.2 is 20%. It's 100 smaller, right? Times smaller than your pre-strain. So that shows an advantage because that means okay, Barcode denomination can generate a smaller peak strain. So that's why it's not easier to get a fracture. Okay. So that's the message I want to give here. But I just show you all these denomination things, right? What's happening, intermediate state, right? We did an experiment here. It's very simple. We have an equal flux. I stretch 500%, so that means 6 times longer, right? I put it in strong, and then I just use a tape, right? I just use tape and then to tape tape in the middle, and then I instruct to slowly to release, right? You can see when I slowly release, you can see the blisters comes out sequentially one by one, right? Finally end up with a periodic structure like this. If you take a look at cross section, the evolution of the cross section geometry, you can see in the beginning, right, you get one blister comes out, and then so this shape is like a sinusoidal, right? And then you go like 50% and something. You see this is we call it elastic shape. This is a jigsaw-like shape, right? That means there's a transition. So in terms of deformation mechanism here, we propose a 3-stage deformation mechanism, right? So when release a little bit, right, gonna be that's buckling occur, right? And then we'll keep compressing, right? That's a moderate compression, you have a sinusoidal wave. And then when you keep a large compression, you're gonna go the elastic shape, okay? So then with this 2-stage, actually we have developed a corresponding model to predict the geometry. For example, here, so the wavelength and amplitude of your blister. So this is the energy-based mechanics modeling for stage 2, that's sinusoidal, right? Assume a sinusoidal shape, the profile here. And then you can write down the total potential energy of the system. So gonna be film from the energy from film, you can have stretching energy in the film and bending energy in the film, right? And also have strain energy in the substrate, also adhesion energy, right, from the interface. Now you can do the summation and then do the minimization of total energy, right? And then you can find out, finally you can end up with this. This is what we got here. We find out the data, right? So data is the wrinkle, the blister wavelength, right? Amplitude H, that's, you see, that's a H amplitude. If we take a look at this formula, we can see, so the wavelength is proportional to the thickness T, and the inversely here is the tau is the interfacial toughness, the strain, right? With related to the modulus of a film. So here is the same. The amplitude is also related to your modulus and also the interfacial toughness here. So now we apply this model to match with the experiment. This is this curve is our model prediction. It fits very well actually with the experiments. It's validated our model. And now we move to stage 3, right? Think about stage 3 is stage 3 is like a elastic shape now, right? It's not a sinusoidal shape. So we use another other way energy method here. We just put a beam here and then just push 2 ends, and then similarly we can find out the elastic profile. We can predict the elastic profiles, right? So this is a profile. This profile is a function of the elliptical integral of the function here, right? So delta and H. So you can see. Let me show the results here. So for example, you can compress 30%. This is 30%, and then you keep compressing. So for example, for the red one, right? So the red one, this one is 70%. And then you keep compress, you can see they become contact. That's interesting, actually, become contact with each other. And now you see now we apply this model, to overlap with our experiment. See the figures, right? It's overlap very well, actually. So if you do this, if you just assume sinusoidal, right, prediction, you see here, I mean, it does not agree well, consider well, because the top here, right? This is very sharp, but here is round. So why, if it's sharp, think about if this is a ribbon, right? Nano ribbon, silicon nano ribbon. So on the sharp, that means smaller curvature, right? Larger curvature, you're gonna have a much larger, higher strain, right? So that means you're gonna crack first. And then we do observe this. This is our model here. You see, this is our model. We can predict the maximum strain in the film. So the y-axis shows you the maximum tensile strain, and the x-axis is the compression strain, right? And now you can see if your profile of the blisters takes the sinusoidal shape. The blue curve is the sinusoidal shape, right? You can see with increase of strain, right, go very high. Here is like 9%, 80%. But now if you could take an elastic shape, see the red curve here. Elastic shape is go very low, right? So especially when the strain is very large. See, and this experiment data actually agree with very well with our experiment here. You see, this is only like 1.3. So we're gonna do the simulation here, and then that's great, right? So that means elastic shape definitely is better than the sinusoidal shape. And then we do a proof of concept for the stretchable electronics here. We just use gold here. This is a bulk denomination gold films and 80 nanometer. And then we'll put a wires and silver paste and to measure the resistance change with your applied strain, right? We can see you can apply like a 150%, and then after that, the resistance started to increase. So that's reasonable, because before, right, it's compact, right, and a shortcut. And now you stretch and then to make it, to make it elongation and then to lose the contact. In this case, the resistance change a little bit. And then we also do the cycles, because we apply the 100%, 200% strain and do cycles and 200 cycles. It doesn't change too much about electrical resistance. It shows we can maybe potentially we can use this to design structural electronics. Okay, so that's I think that's for the second part. And then I'm gonna move to the structure instability here. I'm gonna first talk about akigami. Akigami, right? We know origami. Ori means folding. Gami means paper. So what's the difference between kirigami and origami? Kiri actually means cut. You can just use a scissor to cut or laser cut to cut, right? So you can have the line cut, you can cut out that, right? So that's the only difference. You can introduce cuts and the folding together. That's kirigami. What is the advantage of kirigami? For example, you have a piece of paper, right? And then you can introduce the parallel like slits. That's like line cuts. And now paper itself is non-stretchable. Now you can just after you introduce the line cuts and it becomes super stretchable because of the outer plane buckling. Because there is, so you can see this structure become buckled outer plane. This we also call it tilting outside, right? So they use this idea apply to graphene. They can even cut graphene to make graphene super stretchable. And you can apply to nanocomposites, and also you can make a cut out, right? You can fold and then to hide the cut out, right? When you fold up, so the cutout is missing here. You can it's hidden, right? You can use to minimize material waste. Other researchers have applied this idea for the dynamic solar tracking. You can apply the solar cell to this kirigami structure, and then you can change with the light and then to increase the efficiency. Also, you can do the mechanical self-assembly, right, to 2D to 3D structures, and also to conformable electronics if we have those kind of cards here. Okay, so but actually, when we take a look at this simple cards here, so this is a project done by my students, Yichao Tang here. You see here, right? I mean, if you stretch, you stretch to the right, it's to the right, gonna be clockwise, rotate, stretch left, counterclockwise rotate. If you're stretching both ends, you see in the middle, that's a defect, right? That's what we don't want. And then we're trying to say, okay, what's happening? Why you stretch, different ways and then generate different, tilting directions, right? And then we go to FEM, we just run the linear perturbation analysis, standard buckling analysis. It gives us the eigenvalue and eigenmodes, right? You can see this is the eigenmodes, one eigenmodes, the other eigenmodes. You can see this is the eigenvalue, the critical buckling strain is about 0.042. Here is 0.045. If you compare these two with what we observe here, right, exactly the same. We have the same orientation, but this is a double orientation, is different inside, right? So that why? Because these two buckling strains close to each other, so that's why it's gonna get confused here. So how we can get rid of this kind of defects, right? We have a proposed idea here. We just introduce a notch. See, these are the junction here. We have a notches here, right? See, these white spots. And if you start introduce notches, you actually have break the symmetric deformation. In this case, the tilting direction, the bending direction is all determined, right? So no matter which way you are stretching, you're always clockwise or counterclockwise, depends on how you do the notches here. Okay. The other thing is why we introduce the notches, because think about if you apply it to the thick panels, right? Think about a wood, thick panels. Now, if you introduce the notches, actually can help you to reduce the critical buckling force. So that means you have a smaller force, you can stretch this open. Okay. So why we should care about the tilting direction? Let me show you one example. For the energy envelope, this is a real building, in Germany. So they call it a dynamic shading project. So what they did here, they have put the shades outside the buildings, and then the buildings can automatically change the rotating or tilting directions to reflect and absorb light, and then to block sunlight, for energy savings. When we look at this, right, if we bring up our kirigami things, actually it's very similar. It's exactly the same. I can use my kirigami rather than these bulky things, right? Kirigami here is very similar, right? I can use this to block sunlight. Why not? Because I stretch, right? The 9 cards are open, and then when you release, just closed, right? We call it the adaptive. But when we do the, adaptive building envelope, right? Definitely we don't want to use a motor or like a hand to stretch, right? We want to make For example, we want to make a materials respond for temperature. How about, temperature increase or decrease, and then the cards are gonna open, and then to block sunlight, like to absorb sunlight or block sunlight like that, right? So that means how to make this guy become active or responsive to stimuli. So here's our ideas here. So instead of latches, we attach the tapes. These tapes are heat shrink tape. So that means when the temperature increase, the tape gonna be shrink. These are attached to the paper, so the black parts. So you can say this area, this is bilayer bending, because this guy's a shrink, so the paper does not shrink, right? In this case, you can generate bilayer bending, and then you see this is what happening here. In front and back view, and you see it's gonna be open by itself. Let me show you some example here, right? This is in the oven. We have the tape here and the increased temperature from room temperature to 65 degrees C. They open by itself, right? 5% strength give you like 80% expansion here, single orientation. I can attach a different orientation, for example, for the tapes, right? I can go a double orientation, like what you see in the defects there, right? So you see, this one, you see the top one is a clockwise and the bottom one is a counterclockwise rotation. The interesting here, I can stretch first mechanically, and then clockwise rotation. And then now I put it in the oven, increase the temperature. You can see the tilting direction reverse, go to the other directions, counterclockwise. Okay, so this is dominated, is proved by our simulation here. First, I stretch, right? Give you one tilting direction, orientation. Now I increase my temperature, see? You're gonna be flipped very quickly, right? So this is, in this way, right? Think about when you put the shades, the inside and outside, you have a different reflective materials, right? And then they're gonna be play with different roles. So that's why we care about this kind of tilting orientation here. And now we go to our collaborators, in architecture. So they did a simulation for this to do a proof of concept. You have a buildings, right? You have the windows, and then this window, nothing cover here. And then you put the envelope, this guy's envelope, and this is akigami envelope here, right? And then they do the simulations. This left column is the base model. This is a proposed model, right? You can see when this is happening in December in Philadelphia when the sun comes out, right? So you can see it's very bright. So in this case, you should put your curtains, right? And then put your curtains and turn your electricity, turn your lights on for reading. So in this case, you want to see that's your that's how you can consume electrolyte light, right? But if you use this model, right, you can see, the sunlight comes in but diffuse very evenly. In this case, right, you don't need to turn on the lights and save the light. See, this is a 307. You can save like 375. The difference is 26, right? Definitely, this guy is all cooler, right? So cooling is very good, right? So, but it's not for heating. But overall, if you summarize the energy consumption over the 1 year, the whole year, annually, you're gonna save a lot, compared to the base model here. So that's maybe it's convincing for you guys. We can use akigami for building envelope adaptively. Okay, let me show you why we call this this is a building envelope. You see, you stretch, right? It's gonna open loudly, wider, and then just close and then close that, right? It's like what we did for the blinds here. Okay, so now if we go beyond, right? So now we're just doing just 2D cards, for example, here. So this project is a collaboration with Yongzhu, where it's an ongoing project, and then it's done by students Yao Hong and sister here. So you see, if you just the cards, right, you can generate this kind of shape, right? This is not how about we can go beyond like 3D curved surfaces, right? Think about, we maybe use this for apply for the, for the brains or for other, tissues. These tissues are some 3D shapes, right? It's conformable and stretchable like that. So now the idea here, let me show you here, I just play from 2D to 3D, just play with a different boundary. For example, this is a positive 2D curvature and a 0 2D curvature and a negative 2D curvature, right? When you stretch, simply stretch two ends. Now you see, you can get a general Gaussian curvature is positive and then 0 Gaussian curvature and the negative saddle shape like that, right? This is a simulation, FEM simulation, very well. If these 9 cards and a stretch to do that, right? So this is pretty good. And now how about we move forward? So now you have now you should have 1, 2, 3, 4. You have 4 panels, right? You have these are all 9 cards. If you stretch vertically, can you guys guess what's gonna happen here? What's gonna happen here? Let me show you, right? Surprising. Okay, if you stretch, actually you can become happy, right? Smiley face. So now how about making this become sad, right? Okay, cool. I can make it become sad, and also I can wear glass for this guy, right? So these are all just showing face changing things. This is pretty simple because each part, actually, these are the bistable. You can play with, the pop up, pop down, right? Pop up, pop down, pop up, pop down. And then you can play all these different facial expression and then for fun, right? And I want to go beyond that, we can go 3D, right? For example, I can go droplets, right? 3D droplets, I can go like a paddle, right? So there's rows, paddles here, and also I can put the bottles, right? So if you want, you can put this flower into this bottle, right? And also like a wavy shape, sinusoidal wavy shape, these are all based the things here. We do develop some models, to correlate the local curvature to global curvature, but the time limitation, I will not go through the details about these designs here. And then move forward here, we're gonna see, okay, what we can do for the magnetic actuation, these akigami things, right? I can just put a magnet here and then just magnet and then to stretch that and you can open here. So this one show I can twist, right? You can generate a 3D spiral shape. And this one's interesting actually is like a robot, right? So like predators, right? You see, this is the rock, right? And now you can move here and then and trying to move a little bit, right? Now it's just swollen, right? And then you can rotate your magnets and then to curl inside, right? To capture that. And after it's done, right, you just release the bone, right? And then put it aside. Okay. So yeah, that's the last part. I'm gonna go for the bistable for the soft running robots. So this figure shows you the velocities. So this is the 2018. Maybe now it's changed a little bit. So the y is the velocity, the x-axis is the body mass, right? If you take a look at this, summarize all the mammals, soft robots, and rigid robots. If you take a look, the purple dots are soft robots. The range, the velocity is about like 0.001 to 0.3 body lengths per second. But if you go to the rigid robots, right, green dots is higher. The mammals definitely these are much higher here, right? So you see that this figure actually give you a message. So soft robots actually is pretty slow, right? So how we can speed up? So this is our idea here. So the idea we inspired by the cheetahs, right? Because cheetah is the fastest land animals, right? So one of the key elements for his high speed is his flexible spine. Spine is not actually, this guy is not rigid, it's flexible. So you can see, so when it's flexing, right? So you're gonna be touch ground, right? And then with extension, gonna be maximize the stride length and then to jump off the ground. And that's why you can go very high speed here. So by this one, we put a spine also to a soft robots. This is a pneumatic actuation soft robot, actually a soft robot, right? This is spine. I make this spine become bistable. Keep in mind. So the spine of a cheetah is not bistable. Okay, so we just use a bistable one, and then this is how we did the spine here, right? I just have a spring. I pre-stretch a spring and then the two links, right? So like two links in the middle, and now this guy become bistable, right? And then you can pop up, bend up, bend down, and then very quickly it's a step through. We call it step through, right? So because this spring gonna store energy and then to release. This spine you can simulate the skeleton, right? And then this is we have the soft bending actuator. This is pneumatic air. This is similar to the muscles, right? So muscle, when you pump the air in, they can bend up and down to drive the bicep happens in the spine, right? So this is how they happen here. We pump the air. So this is the energy landscape, the energy versus the bending angle, right? You can see in the middle, definitely in the middle, the bending angle 0 is unstable, right? It's a two stable states. Either you bend up, bend left or bend down. These are two stable states, right? And then you can go when you pump the air and then overcome the energy barrier and then start to step through. Okay, so let's see what happened here. So there's the 3 demos of the prototypes. One is we call the bistable hybrid. That means you have both spine and a spring. Okay, this is real time. And then the middle one is a soft one, is a no spine, no spring here. So this is monostable. If the third one is a hybrid, this is a with spine but without a spring. And then just remove the spring here. This is also monostable. This is the slowest one, right? So you can see that one is a 2.5 body length per second. Average is about 180 millimeter per second, right? So pressure will only like 30 kilopascal. Actuation is only 3 hertz, right? So this is a weight, and this is the length there. Okay, so what's happening there, right? So then we compare, go back to check, right? Compare we call the leap robot compared to previous one. So this one is a 2.5. It's like at least like 8 times faster than the soft robots here. And then let's take a look at slow motion. So that's what happened here. That's why we call it like a Cheetah Inspire, because because they can jump off. They can jump off and then touch ground and jump off their 4 feet, right? Because this is similar the energy storage and energy release, right? So, but think about, right, our legs here compared to his leg, and our legs are passive. These are just, just 3D printer things, right? We didn't do anything. We just use the spine and to achieve a high speed. If we make this guy also bistable or store energy, can run faster, right? And now we do the measurement for this actuator. We measure the block force, the force, and then also make the response time. You can see, right? So this is the blue dot, is the bistable one. It's much higher than the softer one, the hybrid one, right? So that means bistable enables over 2 times higher force, right? And also think about your swing motion from left to right. If you go soft and hybrid, it's gonna take like 2.5 seconds. But for this one, right, for bistable, it's only take like 0.8, less than 1 second. I'm gonna show you here is 3 times faster than the stable soft actuator. The step through does need some time to occur. This can go very fast, like 50 milliseconds here. And then we show the advantage here. So 3 robots, right? Bistable hybrid one is this is the slope, right? It's about like a 17 degree. Right? This one you can see can climb the low, but these 2 they fail because they have smaller forces to generate. And then how about we put this guy, in underwater, right? So if it's underwater, you're gonna be flip 90 degree, and then you can see attach a fin. This is our bistable one, right? Attach a fin to accelerate, right? You can see what's happening here is bistable one, right? That's the winner, right? 0.78, and then soft one and the hybrid one, that's the slowest one, right? If you put the velocity with the frequency, actuation frequency, because you pump air out and out, that's the frequency. So you see the velocity here, mostly, right, that's the previous swimmers, right? Mostly you can see this line. The means linear line, that means the larger frequency, the larger the frequency, the higher the speed, right? For our case, I want to mention here, so I can achieve a high speed at a low frequency using bistabilities, right? So that's the advantage of bistability here. Okay, so to conclude my talk here, so I'm gonna bring you several examples. Hopefully I have convinced you here. So mechanical stability actually can occur at all scales, at both surface and structure levels. And also the mechanical stability often accompanied by the sudden shape change, right? When you respond to different external stimuli, which could be leveraged for achieving unique properties and functionalities, right? I do see that a comment actually when we get this Cheetah Inspire software published, right? We get news report and then we put the videos on YouTube. There's one comment say, okay, this guy is not a Cheetah, this is an inchworm. Okay, I just want to show you, okay, this is not inchworm, this is between Cheetah and the inchworm. I will replace the lag, right, with the spring, because the spring can store energy. This is a 1/8 slow speed. You can see it's really, you can run like that. Okay, so the other slides, I want to thank my students, because all the credits and all the hard work goes to my students. They work very hard. So here, this is my college students here, Yinbin, Yingdi, and Yao Ye working here. And my 3 alumni here, Qiuting, Gaojian, and you can see each how they are working on the soft robots and the bucket denomination things. And then also I would like to thank the collaborators, Yungju, and also from Penn, Drexel, all these different collaborators. I just list a couple related to the project here. I look forward to more to come. So last but not least, I want to thank the funding support from ASF, ARL, so North Carolina State, and also Temple University. Thank you. I would like to take any question if you have.
All right, great job, G. We're open to questions. I think we have 10 minutes left. So feel free to, Yang, you want to start? Yang,
okay. Yeah, very nice talk. Very nice talk, Jie. I think you touched all the topics. They're all interesting. I have a lot of questions. I will start with one on the delamination, on the bucket delamination, right?
Okay.
So, well, actually twofold the question. So one is yours is a spontaneous delamination, right? What John Rogers has is a predefined delamination.
Yes.
So would you compare the two? can you comment on, let's say, any advantages in terms of the maximum stretchability you can achieve? Okay, so that's sort of the first one. And the second is how repeatable is this spontaneous delamination in terms of the locations of the delamination and also the sequence of the delamination?
Yeah, both are very good questions. So the first question, right, to answer your first question. So if you take a look, right, despite, even, right, we are doing the different silicon. This is a single silicon right here. They can, for this one, right, can only stretch like a 53%. I can see that's the crack, right, in these directions. However, in our case, actually, we do see, we can stretch, 120%. I mean, this is let me see if right, that actually we have enhanced like twice. I mean, compared to their method. Also, like I mentioned, right? So their method is complicated. So for our case, for PDMS, you don't do any. You just do like a little bit of oxidation, on the treatment for the surface, and then just do the thermal deposition. And that's pretty easy, and you can realize that, right? But that's a thing for the first question. And the second question, that's the cycles, right? How many cycles, and then actually we can go. I think we do have one slide to show for the silicons, if I can find out here. Oh, I don't. I didn't put there. So we can go like at least hundreds of cycles for this. So for these silicons without the cracking there. And then if you further to answer your question here, if we go to the denomination, so if we see here, right? So if we see this figure, actually this shows well. So you see, right? Everything is cut inside. You see, this is cut inside. So that means this spot actually is fixed. So that means when you stretch back, it's always, that's the adhesion size. It will not move. It will not slide. So that means it will not move to left and to right, and then gonna anchor. This is more like an anchored point. So that gonna be explained why we can generate high cycles. But the worst thing, right? So one of the bad thing about this, right? Like I show in when we measure this, so we do see, because it's all get a contact, right? See, I mean, you see here, right? It's all get contact, and then it's a shortcut, right? Short circuit, like that, right? So you have low resistance. But now if you stretch back, come, it's apart from each other, so electrical resistance increase a little bit here. Do I answer your question?
Yeah, part of. How about the repeatability? How about the repeatability, right? Does it repeatable? But I think you kind of answered, because you said it anchored, right? You have the anchor points.
Yes.
But the question is why they anchor at those points, right? The surface should be the same everywhere. So you did not do any treatment, right? John Rogers did.
Yes.
So why they anchor at those points?
Yeah, I don't know.
Okay. No, I think maybe something happens during the deposition, and
maybe.
because also we recently actually used this approach to develop a stretchable silver nanowire conductor. That's why we actually found is in our case it's not repeatable. Actually, the delamination sites are not repeatable, because in our case it's purely van der Waals bonding. I think in your case, I don't know, it may not be purely van der Waals bonding, because during the deposition, right, you have high temperature. You may have some bonding formed, maybe preferably formed at certain places. That's right. But in our case, every time when we stretch release, actually the pop-up delamination occurs at different points. But eventually, you will form sort of uniform patterns. If you release, if you have a larger pre-strain and then you release totally, you are going to have all of them densely packed.
Yes, I agree.
But yeah, this is a very, very good point. Yeah, very, very, very interesting topic. I will let others ask questions.
I'm going to say, Young, I know that you're next door to G, so you can.
Yeah, I have plenty of time.
Yeah, sure.
Any other questions?
Thank
you. Feel free to ask questions.
Hey, can I? Sure. This is Xiangling. Hey, Jay, I missed your interview talk, so I have to catch this one. It's very interesting work. I have a question for you about your different structure. How about the load capability? You're talking about an actuator, or mostly we're not just talking about the stroke or speed, right? We should also talk about the force torque output. Do you have any comments on that?
So which one? Which are you talking about the bistable software one? Or
Well, give your last the soft robot as example.
so this right? This is a dynamic. This is a dynamic blocking force. So that means you have very fast, right? Snap through, and then you can get impact, and you can put a force sensor to measure the forces. But see here, this is around like a 2.5 Newton. So this is about 2.5 Newton, and then the I mean, right? So the block force may be just one parameter. The other thing maybe more interesting is the torsion, right? The torque, how my torque is generated. We have no data about that, but this force actually depends on your how much strain you have pre-tension your spring, and then because that's the case, you release your strain energy and then to generate a snap through.
Yeah, that makes sense. I thought that there might be a figure of merit, in terms of what's the value of mass, what's the strain and what's the load you can carry to evaluate a actuator or actuation.
Yeah, agree. That go to the device level, right? So the overall performance. The other thing, right? So that's I would say that's some limitation because these guys, you see those tubes, right? I should pull these tubes because without tubes, right, I cannot pump air in, right? So that means, okay, somehow I should go untethered, right? So it's autonomous. If I put everything together and then it should be run like by itself, like that.
Yeah.
Yeah.
Yeah. A lot of work to do,
Yeah. Yeah.
Very
yeah,
interesting.
I have a question. So,
yeah,
so you showed that it goes up and jumps up and moves forward where you get it compress and expand, right? What about sideways? If you add, how do you add like if you want to turn, can it be created with the concept that you're talking about? Because it's a completely different adjustment to the design of the system, right? That you're looking at.
Yes, you're right. So if we want to go, right, if we want to go make a turn, for example, right, I make a left turn, right turn. So that means because the spine, they can only like up and down, right? But that's the work we've done for the feet, for the 4 feet. So that means, for example, if I replace these 4 feet with like very similar like a bistable things, right? So I can tune this guy become monostable or bistable. In that case, right? For example, I make this guy weak or this guy strong, and then somehow it could be help you to turn left or turn right. Like
so you cannot make those legs stiff anymore. You have to make the legs compress and expand too, right?
Yes. Exactly.
That's the only way to do it, right?
Yes, I think so. That's the only way we can do it because
so one go like that, back press down and.
Yeah. Yes. That's I think that maybe that's the only way. I
mean, there's maybe the easier way, not really the easy way, but easier way.
Okay. Yeah, I agree. Yeah.
All right. Have any other questions? One more question.
Yes.
Hugo, go ahead.
2 questions. The first question, you talk about, I think the first topic, and this slide 19 specifically. You mentioned that you increase your strength from the gold, also the silicon, right? The fracture strength.
Yeah.
I think because if we look at fracture strength, is the material property, and then the enhance of your apparent strength is due to your residual stress inside of the body, right?
Yeah.
So overall, I looked at top majority of your talk are related to either the buckling or snap through. If you look at conservation energy, right? And either you're talking about Cheetah jump, basically it's more sort of like releasing your energy, right?
Yes.
Okay.
Yes.
In large deformation, that's what you're looking at.
Yes.
And second question, since you use all the formula related to continuum mechanics, but I guess in your domain, you're looking to tens of nanometer. So you'll still fit quite well using the continuous mechanics, right? Principle.
This is a really good question, right? So like you mentioned, right? So there's a van der Waals forces, maybe, you know, the adhesion there, we do not consider there. So all goes continue, we neglect all these nanoscale, the scaling effect in our model.
Okay.
But by the way, we do validate our model through experiment. I didn't show the details, but it does, I would say it does, you know, it does do, that does agree, you know, with nanoscale experiment. So
Did
because
you
the
see
model,
a little bit stiffen effect due to the nano region?
yeah, this is a good question. So we also maybe, you know, we think about our model because this model, like I said, is a continuum based, right? Continuum mechanics based. So if your film goes to nanometer, if it's go to less than 10 nanometer, that's the size, right? That's the size of effect occurs there. So that means maybe your silicon itself is not fragile anymore. It's become, you know, maybe it's more stretchable. You can stretch more than 5%. So that means maybe we are wrong here, but maybe we are wrong here, but we do see the cracks of the silicons
Yes.
in our experiment.
Hey, G, there's a question from Brendan on the chat. He's asking, in your Kirigami blinds, is the thermal actuation cyclic and repeatable?
Okay, cool. This is a good question. You know, for the paper itself, right? If you just use paper or like plastic, right? That one, if you stretch millions of cycles, it's gonna work well if not overloaded, right? But the other thing, right? So because you now attach some thermal responsive materials, so that means because think about if you put outside, right? Every day you get a sun side, and then you get everything gonna be there. Maybe you're gonna see some material degradation there, but this is just a concept. I will say this is just a concept, right? We can use that, you know, to collect water. Even you can do the coatings on these kirigami things, and then you can collect water like what we did for hierarchical wrinkles, right? So that's I think we gonna have some issues there.
All right, so I want to call it close here. I think Jay, very good talk. Appreciate it. A lot of information on some of the new stuff that you've already started since the last year here. So I think it was great to hear what you've been doing. I think everybody does appreciate what you're doing in the new area of research. So I'm going to call it the end of the seminar, and thank you all for attending and appreciate it, and see you all at the next seminar. Thank you.
Thank you. Bye.